check.
Oh, you should probably look at your stream.
Cool, we're good. Thank you, Kat. All right, lads and ladettes. So the format is going to go as follows. If you have any questions, please wait till I finish the slide, and then you're free to ask, or if you want to save them up for the end, we're good to go. There'll be a Q&A at the end. So this is going to be on classical physics and leading up to relativistic physics. This is going to be kind of a history overview, going over what a reference frame is versus what a coordinate system is, and what the physical interpretation of the mathematics that's being put forward for physics and cosmology is supposed to mean. So we're going to start with the Newtonian philosophy of absolutes, and then we're going to move into the relativistic philosophy of relativity. And we'll do a comparison there, and then we'll go over a couple of experiments using what we learned about reference frames to see if the current theories are any better than the previous ones. Okay. So reference frames versus coordinate systems here. So to give some basic definitions and to give you some idea of how I want you to conceptualize what I'm talking about as we go through the slides, you'll notice these are color coded. So red is when I want you to think about something being just abstract mathematics. Blue would be a reference frame. And when you think reference frame, don't think human, think where the instrumentation is, where the measurement is being made. That is the frame that we'll be using, or when we're talking a reference frame. So a reference frame is comprised of a coordinate system. It'll describe the dimensions, etc., that kind of stuff. But when we're talking about where the instrument is, that's going to be a specific way to refer to that. And then in relativity, they even say here on the Wikipedia, they call it the observational reference frame, meaning where the observer is. And this will be an important distinction as we move forward here. So Cartesian coordinate systems can represent many different geometric shapes, and we'll go over some of those as we continue. A reference frame, you can think of it containing an observer with a clock and a measuring rod. So we're going to have instrumentation to take measurements. The human part isn't necessary, but I like to conceptualize a person using the clock or something. I don't know. Makes it easier. So anyway, in yellow, text will be when something is in motion. So, or when it's a non-inertial frame. So in relativity theory, actually, no, I'm sorry. That won't be for non-inertial frames. Just when something's in motion. Anyway, in relativity theory, a reference frame determines the relationship between a moving observer and the phenomenon under observation through Lorentz transformations. So that is the prescribed method in relativity theory. When we get into that part of the analysis, and then time and distance are defined as relative functions of velocity squared over the speed of light squared for the moving observer with respect to the source emitter. And in Newtonian physics, the reference frames, time and distance are absolute. They don't change as a function of velocity. They are independent of the motion. And we'll come to understand what those implications mean and how physics was built upon those principles. But before we get to that, we're going to take a look at some cool coordinate systems. Coordinate systems define spatial parameters, and they're defined by a fixed axis. So the x, y, z, t that we looked at earlier, right? Those are all going to be Cartesian coordinates for what's being described, and we're going to look at what all can be represented with coordinate systems. And Shane likes to say we live in coordinate system simultaneity because of the conical, rectangular, and spherical projections are all equally valid all at the same time. Well, this book is going to show us some different transformations and how they're all the same here. So we're going to start with a rectangular coordinate system here, standard XYZ. And as long as a common axis is shared, primarily the Z axis for this, you can do a transformation to always show the equivalence between these frames with just a simple angle transformation here. So when you get into the cylindrical coordinates, the way that you get back here will be shown in brackets. So this will be how you do the transformation to get back. So we can do elliptical cylinders. And again, this is all intersected by the plane here. So you can always get back to that relationship there. Again, with spherical coordinates, ellipsoid or prolate spheroidal coordinates. Very cool. Parabolic coordinates, conical, para, paradoidal, oblate spheroid. Anyway, as you're going through all of these, they're all the same. They're all equivalent. Um, then he goes over the rules for transforming and all that. But anyway, just to kind of show you the different things that can kind of be described. But remember, when you're describing a coordinate system, is it arbitrary or is it describing something where where a measurement took place? Right. This is going to be the big distinction here, and especially when we get into the relativistic theory, where in the Newtonian theory you could invoke like a fictitious frame to describe things, but in relativity theory, we're given specific parameters for how we're supposed to handle things. So to guide us through, we're going to refer to this textbook from called "The Principles of Dynamics" from Donald Greenwood. He gives a great analysis on the history of classic physics for dynamics or predictions, and he goes over reference frames and the concepts of absolute time and space and stuff. So we're going to refer to this for our history lesson on the philosophy that was given to us. So, mathematically defined for reference frames as a rigid set of coordinate axes, so that x, y, z, t coordinate axis, all fixed to a stationary, non rotating point. Now, when Newton derived the laws of physics, he wasn't sure where to put, like an absolute space for his concept, where because they consider the Earth in motion, so it would be a non inertial frame for rotation. But, the laws of physics apply uh, in this frame. But anyway, but for philosophical reasons, he didn't consider the Earth as being the rest frame, so he put it out in at the center of the solar system. This is what we're going to learn here, and then for different scales of prediction, they kind of talk about how you would have to use a different reference frame. So instead of using the Earth at like for like local measurements for something larger scale, like they're saying like if you're doing like a missile launch or a satellite, you would want to use the center of the Earth as the frame, and that's a fictitious coordinate system because there's no actual observer at the center of the Earth, right? But they're using this fixed reference point for it to be relative to because they say it's more accurate that way, right? So they don't want you to conceptualize the Earth as the frame, but like maybe this like hypothetical place at the center of the Earth you could use that'll be stationary with respect to the fixed stars. So that's kind of how they philosophize it and justify using it. So it's like it's a matter of scale for which reference frame you want to use your description. So that's kind of how they lay it out. Now, for something like, say, they would say if you have something in orbit, right, you would want to use the barycenter. So this would be the gravitational equipotential point between the sun and all the other planetary bodies. So something in Newtonian physics with absolutes, you can do mass addition, which will be important later. Give me 1 second. Got to get some water. So you can do things like add up all the mass in the solar system and then have it be versus the mass of the sun. And for example, with mass addition, right, you could take 5 pounds and you could add 15 pounds to it. And then now you have 20 pounds, right? So pretty straightforward in that regard. So let's see. So the conclusion here is absolute space exists, but just not sure where it exists, where to put it because of philosophical reasons. And then, real quick, before we continue on with the dynamic principle book, we're going to swing by the how and why and basics for mechanics, where a quick dialogue is given on reference frames and not to confuse it, where like it doesn't mean that that's where the human is, that's where the instrumentation is. I just wanted to be really clear about that because this leads to a lot of misconceptions, apparently, even in higher levels of academia when they're talking about reference frames and coordinate systems and whatnot. They are specifically talking about where the instrumentation is, where the measurement is being made, and he just wanted to make that clear. So they do this anecdotal back and forth between a professor and a student. That's a pretty fun read. So you can check that out on Google Books. It's on page 115. Um, let's see here. Is there anything that I'm missing? Nope. Good to go. All right. So absolute space. What is it, right? It's this fixed coordinate system that all things are going to be relative to. So Newton determined, which we'll get into how he determined this, that a reference frame that is in uniform transitory motion, his equations hold good in there, and there's not going to be any inertial forces acting on that frame. And you can use that as an inertial frame. So he's saying that if you're uniform transitory motion, that's just as good. But for rotation, when he did the Newton's bucket, he came to the conclusion that there had to be an absolute space, so he just didn't know where to put it. And apparently, he wasn't opposed to one for transitory motion, but it was never really discussed much. So there's an inertial frame at the center of the universe, right? Some mathematical construct that's defined by the the gravitational potential between the sun and all the other planetary bodies and their positions and distance away from the sun at any given time. So the so the conclusion from the Newton's bucket thing, which we'll cover here in a second, is that rotational motion is relative to an inertial frame. But again, he didn't want the uh, Earth to be the inertial frame, so he thought that it was at the center of the solar system. Um, so, all right. So, absolute time. Now, this is how he came to the conclusion that an inertial frame can be defined as being in uniform transitory motion. So, in Newtonian physics, there is velocity composition, where it's just basic Galilean velocity addition, but that works on the principle that that all observers have the same time. So when you do a summation of their relative velocities, if there's no change in them, you can if you take a time derivative of that, you would determine that there's no change in time between them. So from that, you would determine that there's no inertial forces acting on them, and F equals ma would apply in that. So to give you like a scenario where this would apply, say you have an observer in a train, and the train's moving at a uniform constant velocity. It's a closed system, and the observer in the train is juggling balls. He's not going to experience any inertial effects on him. The balls aren't going to, move to the back of the train. He's not going to move out from under them or anything like that, right? So that's kind of what they're putting forward when they talk about a change in velocity over time to determine, if because that would determine if there's inertial forces acting on you. So anyway, that's how they came to the conclusion to that. So this is based on the concept that time is independent of the motion of the observers, and there's some absolute frame, some background thing that all motion is relative to. Not necessarily a medium in Newton's case. Like I'm not, but just something that this is all relative to, right? This kind of what they're is the backbone of how they're building this whole thing. So relative to what? Well, everything that was done on the Earth when all this was defined and experimentally derived and mathematically derived. So I would say the Earth would probably be a good starting point. And we're actually going to get into some dynamic analysis to show that the lab frame is the only frame that makes the correct prediction for the laws of motion in regards to dynamic analysis. So when we get into conservation laws and kinetic energy potential and all that kind of stuff, we can show that the stationary lab frame is the only frame that makes the correct prediction. All right, so earlier when I was talking about the velocity addition stuff and how they would take a derivative of the relative acceleration to determine whether or not if there's a change in time, to determine if there's an inertial frame. This is what they lay out. So we're just looking at a coordinate system here of two particles in relative motion. Even if their velocities aren't the same, when you add them together, and then if you do the same thing again and there's no change uh, between the two, then they're in uniform relative motion to one another, and they're both in inertial frames, and Newton's equations would hold true in them. And that's how they present the analysis through this like one-sided perspective where they have a scenario where Newton's equations for inertial forces acting on you holds good, and you can make dynamic predictions of motion um, based off of not feeling any inertial forces or having to account for them. So again, when we get into the dynamic analysis of it, we can show that that's not the case. Um, and this is contradictory to the idea that the laws of mechanics hold good in this frame that's been derived as being in uniform constant motion, and it's equivalent to a rest frame. Now they didn't even believe in like a rest frame, but they're saying that all of these frames are equally valid. And that's actually later what's put forward explicitly by Einstein. So if all these are the same, then they should all give the same outputs when we do energy conservation and uh, kinetic energy analysis and stuff. So anyway, just to kind of reiterate here, the assertion is that dynamics is valid by choice of convenient coordinate systems with respect to some other preferred frame, possibly the stars or the barycenter. Dynamics is only valid when using the lab frame, and relative motion is only true explicitly when you're doing kinematics, when you're not accounting for actual forces or anything like that. So on the fundamentals of absoluteness, what do they do with all this, right? We've got this nice philosophical framework of absolute time, absolute space. We've got some nice calculus and some nice algebra to derive inertial frames from. We're doing great. What else can we do with it? Well, with time, length, and force, and making mass and force a dimension, you can um, build off of that. So off of those three units, length, time, and force, they got, well, and you get mass out of that. So they have velocity, acceleration, energy, angular velocity, momentum, inertia, linear momentum, angular momentum, all these things that they use for analysis, like for real world things that, give actual properties to things that describe things in a meaningful way. Like for example, like how much stress you can apply to something before it breaks, how much angular momentum something has, etc. Right? All of these things make predictions based off of these assumptions and how they've worked everything in with ratios and constants. Now, some of the constants don't have to be physically meaningful, but because they can be used as a ratio against, they can give you a calculation that can help you determine whether or not something is true. Um, so we'll get into what that means as we continue on. So a quick definition on mass is that there's no real good operational definition of it. It's very circular and it hasn't changed since Newton defined it. We'll read a little bit here from the text. It says Newton defined mass as a quantity of matter which was calculated by the product of a volume and density. Although this definition may be an intuitive concept of mass, it is not a satisfactory operational definition. It merely replaces one undefined term with another. And so, to give an example of that, to find density, you need mass over volume, and to find mass, you need density times volume, and to find volume, you need mass over density. So you're just kind of doing this circular thing that gives a description of it, but not really telling you what it is. But you can like define its properties through this description. So that's kind of what they're saying there, and this will come into play later. And like I said earlier about mass addition, so you can add mass uh, in this framework. Whereas in relativistic framework, mass will change as a function of your velocity and your energy. Let's see. Yeah. Okay, so here we're looking at a cool image of where the potential absolute frame could be. One of these stars, perhaps somewhere back in here, or over here by the sun, not in the center, but like, close to the center, a little off center. And that's just the philosophy that was put forward by these lads. So when they get into things like describing coordinate systems for GPS and whatnot, they'll use the ECI frame. So it'll be, instead of the Earth, right, they'll use a point fixed at the center of the Earth that they'll come back to later, because it's uh, easier for them to do their transformations and corrections and stuff on the back end. They say so. So when they get to that, they say they need to use this fictitious frame that's at the center of the lab frame, but not the lab frame itself. Um, so yeah, then Mach introduced the idea that mass. Well, I'm sorry. Well, first he introduced that time was an abstraction, and it was only due to a change in a system based on relative motion that was with respect to the entire mass of the universe. So we'll kind of go over what that means as we continue. But we're just looking at the two frameworks that were put forward were, absolute with respect to either the solar system or with respect to the entire universe. And when we look at the actual quote from Mach, we'll see that it's with respect to the Earth and the mass of the universe, which is an important distinction that's not covered in current mainstream. You'll often see it misquoted, but it's all about where to put this reference frame, because we don't want you to think about it as the Earth, even though everything was derived here and started here. It's got to be either like at the center of it or out here by the sun or in these stars. So if we have a hypothesis and a null hypothesis about making predictions or future predictions of motion and satisfying dynamic predictions, like for conservation laws, etc., um, the laboratory frame is going to be the frame that will show that that it makes the correct prediction every time. Whereas other frames, such as the ones that are in uniform transitory motion, will show that they're not equivalent, that a distinction can't be made between them. And so that it's a myth to say that you can just choose them arbitrarily. So to start us off with the philosophical implication here from Newton's bucket, we have Newton rotating a bucket with respect to the lab frame. He applies his equations for centripetal force for the bucket, and he determines that the water in the bucket is going to deform, it's going to curve based on the velocity of the bucket. So when you go over the equation, Fc equals mv squared over r, m would be the mass of the bucket, v would be the velocity component. And if you were to put a fictitious observer inside of the bucket, a little bucket lad, and you spun the bucket lad would be stationary. He would see everything moving around him, and he would predict that his velocity is zero. So when he does Fc equals mv squared over r, he would put zero for his velocity, and he would make the wrong prediction. So Newton said, "Well, you know what that means? Sorry, your mic's going off, buddy." So Newton says, "Hey, you know what? Uh, there must be a preferred frame that this is relative to this, but it's not the Earth. It's going to be in the fixed stars, or I'm sorry, it's going to be in the solar system." And then, of course, that's where Mach said, well, it's with respect to the entire mass of the universe, the mass distribution of the universe. Um, so that's the overview of Newton's bucket and the bucketeer frame. And then so this is for circular angular rotation, right? Now we're going to go over the linear acceleration variant. This is Bennett's hiker. So when you do the same analysis for inertial forces felt by the driver versus a hitchhiker on the side of the road, the hitchhiker makes the correct prediction that the driver will feel an inertial force and that he will not feel, the driver himself will not feel any forces. because his velocity is 0, so he makes the correct prediction. Now the driver in his frame makes the, if he's like, okay, I'm moving, uh, he will make the correct prediction that he will experience uh, inertial forces. That he'll feel that acceleration, right? He'll be pushed back to the back of his seat when he's accelerating. Now, if he does the same thing if he considers himself stationary and the hitchhiker in motion, he predicts that the hitchhiker is going to have a force accelerating him, but there's nothing acting on him. So he makes the incorrect prediction there. Um, so that's showing the distinction there for the linear variant. Now that's for acceleration. So now we're going to go over some examples of uniform translatory motion for the analysis for the correct predictions on what forces will be felt, or will the conservation laws be satisfied, etc. So here we have Foucault's pendulum. We have the pendulum frame and we have the earth frame. And we could take the analysis where the earth is doing the work for the to make the pendulum swing. And when you do that, the uh, using the mass of the earth, basically the pendulum would swing off into space. It's not a valid way to look at it. So the pendulum bob swings with respect to a stationary Earth. The frame equivalence, which flopping there, or I'm sorry, the frame equivalence there isn't representative in the energy output when you analyze um, the energy produced by the frames. So there's an unrepresented amount of kinetic energy potential that's not represented there. So when we can do the same thing for the train analysis, because what we can do here is show that the analysis, like the energy of the balls, is missing the velocity component of the train. So if you were in the train, you wouldn't you wouldn't put the train's velocity for your ball prediction. So you would make the incorrect prediction there. Although you wouldn't be feeling any inertial forces on you, right? You could throw those balls up and they're not gonna roll to the back of the train or anything like that. But they do not satisfy the energy prediction for the balls. So only with respect to the lab frame can you do the full analysis to apply Newton's equations. So this definition of an inertial frame being, defined as a frame at uniform constant velocity, and it can't be shown that there's a rest frame, and where is it? And it's like the Earth. The Earth is where it's at. The choice of reference frame taken by convenience is a myth, because when you go to satisfy the conservation laws and make the correct predictions for the energy outputs, it's all with respect to the stationary lab frame.
Mhm.
All right, so we have another analysis here of a biker on a ramp. So if the Earth is stationary, the biker goes down the ramp. You use the mass of the biker, the height, and gravitational acceleration. You can make the correct prediction for how fast and how much energy he's going to have when he comes down that ramp. And if you use the mass, if you consider the bike stationary, use the mass of the Earth to rise up and do it, you're going to send that lad off into space. So the only way to satisfy this is when you're making it with respect to a stationary Earth, showing that these are not equivalent through dynamic analysis. Now, it was proposed at the beginning of this, in this one-dimensional side, through like the perspective of a train, where you would make the correct prediction for forces acting on you. But other than that, we're seeing that it doesn't make the correct prediction in other cases. So to kind of rectify this and the deviation from the change in physics about the lab frame and absolute, right? They tried to measure the velocity of the lab frame, which is coming up soon. But to quickly cover Mach's analysis of Newton's bucket, he says Newton's experiment with the rotating vessel of water simply informs us that the relative motion of the water with respect to the sides of the vessel produces no noticeable centrifugal forces, but such forces are produced by its relative motion with respect to the mass of the Earth and the other celestial bodies. And what he was saying, and what he goes on to argue, is that there's an equivalence between the Earth being stationary and the universe rotating around it. He's saying that that would produce forces when you consider that relative motion, and that would make the Earth oblate and all the things that they assert. There would be a complete equivalence between the two, based on the mass distribution of the universe, which is going to be heavily reliant on the theory that supersedes it when we get into the general theory here. Um, but so yeah, no difference between rest and rotation, mass distance of the stars. So yeah, the distant stars would produce these inertial forces. No proposed like mechanism as to like how it would work. It's just kind of how they interpreted it through the paradigm, that it would just work itself out. So earlier I mentioned that they tried to measure the velocity of the lab frame with respect to absolute space, and a big part of um, the ether framework that Einstein removes is, not only the concept of a fluid medium, but the mathematical concept of a fixed frame, a preferred frame, some absolute frame for everything to be relative to. So in 1887, they following the experiments from Fazal measuring the translatory velocity of water proportional to the square of its refractive index, um, going with and against the flow, they determined that they could also measure that same relationship in air, and the based on the refractive index from a vacuum, it wouldn't be much different. So anyway, they go through their prediction here on how much the displacement should be, and the equation that they used, 2D times v squared over c squared, which is the velocity of Earth, 30 kilometers a second squared, over the velocity of light squared, gives them their change in frequency for how much the fringes are going to displace. Like that will be proportional to the fringe. So when you go out and measure the fringes, the distance between the fringes is actually proportional to the square of the velocity. So that's what they learned from Fazal's experimentation and some other experimentation in between, because apparently, they nailed this equation. It's dead accurate. Later in 1913, when Sagnac does his derivation, the formalism looks a little different, but in modern times, when you reduce it down, it's identical to this original equation from Michelson-Morley, where it's just the length or area of the path length times the angular velocity or linear velocity times the or over the uh, speed of light and the wavelength. So, which is what they use for inertial navigation systems and stuff now. So this interpretation, the measurement is was extremely meaningful, and especially in their interpretation before they decided to like throw out this relationship here and not interpret this as meaningful, um, when they didn't get the value that they needed. So they, following Kepler's laws and Newtonian dynamics, which they um, can algebraically shuffle in, um, with big G and big M, and then derive like a little m off of that, so they can assert like actual dynamics to the sky. So earlier we talked about dynamic predictions, what that means. Well, Kepler's laws are based off of empirical observation, and they're just a ratio of pi over the and the periodicity, which gives them like a conceptualized orbital distance, right? Like the semi-major axis, actually. So that's how they defined everything, like distance wise for the model. And then when you can algebraically shuffle in Newtonian dynamics using the ratios and the same constants of the period with respect to the periodicity, it shows like they were like, "Oh, dude, this must mean that, the Earth weighs this much and the sun weighs this much, and the gravitational potential between them two is causing them to move at this 30 kilometers a second velocity that's predicted by Kepler's ratio." So they were all super excited about this in their paradigm when they started algebraically rolling this out. And then this was supposed to be the test of that, following Airy's failure, where they had a specific angle change based on the velocity ratio. When you change one of the components or when you change one of the velocities in the equation for uh, for aberration, they predicted a different angle change, and there wasn't an angle change measured. So they were like, we're not really sure what to do with that, but we can maybe explain it through some transformations using Lorenz's theory. But then Michelson-Morley came around where they were going to actually measure the wavelength of light. So this is going to be way more definitive because they knew that this displacement measurement would be proportional to the square of the velocity because they already confirmed that with water. So to kind of talk about what the fringe is really quickly, the fringe, right? If you take a light beam and split it orthogonal to itself, meaning at a right angle to itself, in such a way that it either bounces back and recombines or it completes a circuit and then recombines, it should theoretically, if the speed of light is isotropic, meaning there's no change depending on which direction you're facing, then the split beam should go back and recombine and there should be no fringe displacement pattern. So, and what the fringe displacement pattern is when the beam is, if it's out of phase, it's going to create constructive and destructive interference where the wave peaks are going to overlap, or the peaks and troughs are going to overlap. And that's going to create little bright portions that are illuminated and little dark sections. And if you measure the little dark sections, that distance is proportional to the square of the velocity that it's measuring. So that's really important because it's a physical measurement, using a wavelength of light to substantiate a a ratio to a velocity. So that's what they were doing with water when they took that measurement. So they knew that this was a valid interpretation and how this would work. So if they were going to get, when you math this out for 30 kilometers a second, you would predict that the fringe displacement is going to be 0.05 wavelengths. And when they measured it, they got just over one wavelength. And when you square that, that comes out to 6 to 8 kilometers a second rather than 30 kilometers a second. So they were in quite a predicament because now they had a measurement that was outside of like experimental air tolerance because their air tolerance was 2 kilometers a second and they measured 6 to 8. They were way, and they go on to say later in their paper about how Lorentz's explanation that was put forward and Stokes's and Fresnel's that were put forward to explain Airy's failure weren't valid if you use these measurements because they're too big. The value 6 kilometers is too much for their experimental error. So what they ended up having to do was round this measurement down to zero, and say that it was just a nice clean zero here, and that they measured no change in the difference in the east-west directions versus the north-south. And with that, they introduced, they could use Lorentz's theory, which was a static ether theory that said that rigid bodies would compress in the ether as a function of the square of their velocity. So the Lorentz transformation that Einstein uses later on, where he philosophically removes the ether and makes the distinction about relativity of simultaneity versus absolute simultaneity. There's but the mechanism of time dilation and link contraction are present here as the mechanism of motion through the ether as to why you can't measure your absolute velocity with respect to the ether. Because if there's an ether and there's a fluid medium, and if there's a absolute frame for everything to be relative to, then this velocity component needs an explanation. You can't leave this hanging. Uh this is like in the face of your theory, right? So they need this to explain it. Now, Einstein, if we follow the story, just looking at it through without calling into question any of the other stuff that some of us may or may not know about, but if we just follow it as is, right? And here's this guy. So here's this guy Einstein in 1905. He comes through with Lorentz's framework, and he's like, "Hey, if we reinterpret this and say that instead of being on the relative motion of the Earth and the luminiferous ether, we can kind of reframe this and say that there's no ether, right? There's no ether for this to be relative to, and we could say that we could preserve the idea that the Earth is in motion around the sun through the Lorentz transformation, and we could do the transformation from the sun and the earth. We could just say that time and space changed as a function of velocity without saying that it changed as a function of velocity through the ether. So the mathematics for the two are identical, but we're gonna dissociate from one aspect of it so we can move on. And I'm gonna make a couple of clarifying distinctions here as I lay down the preface for reinterpreting the framework and using Lorentz transformations to describe um, these measurements regarding high velocities and light. So in the 1905 paper, he goes in the first page, he lays out how it's been shown that the laws of mechanics hold good in uniform in frames that are in uniform transitory motion. So he says, with that, I'm going to raise a conjecture to a postulate of my theory. So I'm going to build on that and say that my theory will also be valid where Newton's equations hold true. And a second thing that I'm going to introduce, which will be irreconcilable from the former, will be that light is always propagated in empty space at a definite velocity that is independent of the state of motion of the emitting body or the observer. Now, he doesn't say observer in this sentence, but this entire paper, as he goes on to define things, is about the relationship between the two observers. Because remember, we're not going to be using fictitious frames or anything absolute here. We need to keep everything with respect to where the measurements are being made, because on the relative motion of the Earth in the luminiferous ether, well, we're removing the ether component, and now we're on relative motion. So, what on the relative motion of what? On the relative motion of the sun, not the ether, right? There's no ether. So this is going to be very important moving forward, because even nowadays, a lot of people kind of confuse this interpretation and don't understand the significance of what's being uh, stated here, or to make the distinction between the two theories and why they're significantly different. Okay, so, and then he goes on to say that the introduction of a luminiferous ether will prove to be superfluous, in as much as the view developed here will not require an absolutely stationary space provided with special properties, nor assign velocity vectors to a point in empty space in which electromagnetic processes take place. So this will be really important when we get into interferometer experiments, where fictitious frames will have to be used to explain certain measurements. So remember, these effects that are being introduced here are not first order effects. These are effects of velocity to the square of the velocity over the speed of light squared. These are extremely tiny effects that come out of these equations. These aren't the big effects. So when we get to interferometry, we look at first order timing differences in the speed of light, where it should be isotropic. It measures anisotropic. We're gonna how does one explain that? Well, you have to contradict the theory on the face of it in page one to answer these things. But kind of getting ahead of myself. Let me back it up a little bit here. So we're introducing a scenario where Lorentz transformations, a change in time and a change in I'm sorry, change in time and change in time and a change in velocity. I'm sorry, distance, are going to lead to relative length, relative time, and relative mass. So earlier, when everything was built on absolute values of length, time, and mass, now we're going to have mass, time, and length change as a function of velocity, and it's not no longer going to be absolute. When we get into relativity of simultaneity versus absolute simultaneity, in the classic apparent, like the relativity, like a relativity of simultaneity would be an apparent effect, right? Now Einstein's going to propose it as a physical outcome, because spatially separated events in relativity theory are not causally linked to time dependent, or to time dependent frames. So, and what this means is, if the laws of equation if the laws of mechanics and all this hold good in these frames and they're indistinguishable, then the sequence of events that occurs in them also must be indistinguishable. So this is going to lead to something that needs to be explicitly defined as relativity of simultaneity, which deviates from absolute simultaneity, where instead of looking at it as an apparent effect, like a Doppler shift kind of thing, you would be, like they're going to say that this is going to lead to physically different outcomes. Okay, so when we get into, it says here, like, the equations of mechanics, well, which ones? Are we talking about the ones that satisfy dynamic analysis? Because right off the rip, we're already, relativity would already be cooked. But we can, but let's like proceed forward or whatever for a little bit at face value and see what we can learn about the theory and what's being proposed. Um, so again, the entire paper though is about the observer and the measurement, right? The measurement that occurred on Earth that contracted and dilated.
Oh, this, I just asked this too. Has Elon been caught deliberately missing Twitter since 2020?
Second, sorry, that guy. All right. Yeah. So no fictitious frames here. Observational reference frames. Always. All right. So some people will say that link contraction and time dilation aren't real effects, and they don't actually occur in the frame. This is not true. In 1911, Einstein had to go on the record and correct people because if his definition of simultaneity, right, if there is absolute, then these values, these relativistic links and times and masses can't change in like a meaningful way. So there has to be a disconnect from it for him to introduce this, and this means that that simultaneity. So basically, what this means is if your length and time are absolute, then you can't use the relativistic framework. It would be a contradiction. It would always have to be relative to the velocities in question. It can't have an absolute length. So anyway, he steps in to say, to kind of define the parameters of it and say like to be physically meaningful, to give a dynamic explanation to experimental measurement, right? We have to say that the apparatus contracted as a function of its velocity squared over the speed of light squared. And you could go on and measure it, etc. So just kind of to reiterate that, when he goes on to talk about defining time for simultaneity, this is really important because he's saying that time, as you understand it through the classical sense, where you could say an event that occurs for me at 7 p.m. every day is simultaneous with respect to the watch on my hand. If you were in motion and it's 7 p.m. for me and this event occurs, it's not going to be simultaneous for you. And that's the analogy he gives to kind of introduce us in. But then he goes on to say, which I'll read from the red part here, where he says, and in fact, such a definition is satisfactory when we are concerned with defining time exclusively for the place where the watch is located, but it is no longer satisfactory when we have to connect the time in a series of events occurring at different places. What comes to the same thing to evaluate the times of events occurring at different places remote from the watch. So, extremely important because it's going to sound logically incoherent to say that um, a simultaneous event in reality observed by one observer just because someone is in motion, that it actually wasn't a simultaneous event and it could lead to a physically different outcome if their velocity was going fast enough. And even when you get into interferometry, it's actually put forward a relativity of simultaneity for non-relativistic speeds for a simple rotating interferometer, which is completely contradictory because then you would have different physical outcomes at for events that are non-related to a spinning light beam, that have different divergent outcomes that isn't manifest. So that it's not really well thought through. But anyway, this is what's being proposed here, and he has a little special preface down here at the bottom. We shall not here discuss the inexactitude which lurks in the concept of simultaneity for two events approximately at the same place, which can only be removed by abstraction, which is basically saying, think about this super far away as possible, so it makes it easier to digest. If you try to digest it in the form of this train analogy that I'm going to give you here in a little bit, it's going to sound preposterous. You may have a hard time swallowing it. But with enough abstraction, with enough mathematics, we can get to the bottom of it. So anyway, remember the rules of engagement for relativity theory are Lorentz transformations, and you have to show reciprocity between the frames and events, meaning they don't give simultaneous agreement for spatially separated events, i.e., two strokes of lightning, or in his case, the watch and the train aligning at the same time at 7 o'clock. It's not going to be simultaneous for other people. And if the frames have to be made to agree with the simultaneous event in reality, then simultaneity is absolute. And if there's an absolute, then you can't have this fantasy of relativism. So you need the clear distinction between the two, and you have to um, accept that. So to kind of reiterate, causally linked events like your birth and your life and then your death, right? All have to go in order, right? Because they're causally linked. But events that are not uh, linked to you causally will be perceived differently, and you will have in that order that you perceive them in is physically valid. Otherwise, these equations don't mean anything. And for them to be physically valid, um, that's the only way that we could have reciprocity in the transformations. So what I mean by reciprocity, before I move on, is that you have to be able to show that in one frame, due to the frame equivalence, right? When you make a frame stationary because there's no actual rest, right? As they say, you have to show that the effects in the frame that's in motion are shown in the frame that you're using for that stationary in the analysis. So they always want to use the scenario of like the Heflin Keating, for example, where they took atomic clocks around the world in planes. So they're moving at a uniform, constant velocity. They're in the plane. They come around. The clocks are desynchronized, and they're like, "Look, time dilation." Okay, well, the clocks were synchronized with clocks that were left stationary on Earth, and to do the proper Lorentz analysis, right, to do the transformation, you would analyze the clock with respect to the stationary clocks, and the changes that were shown in the moving clock would have to be manifested in the stationary clock. And if they're not, then those frames aren't equivalent. Then you know that clock was stationary the whole time. And the so mathematically you can do that transformation though and show that, but no physical measurement has ever shown that corresponding velocity change in the measurement. So they have a one-sided analysis when they need reciprocity in the frame, which leads to, I'm sure you guys have heard of the twin paradox, where when the clock returns, completing a circuit. So like even if we take the example given by Einstein, where you don't have to have the clock come back and like accelerate and decelerate, it just completes a circuit and comes back. Um, that stationary clock has to show the reciprocal uh, desynchronization, but it's never been manifested. So anyway, hope that helps clarify the simultaneity and the causally linked versus spatially separated for the timing, because they'll say that, well, that would violate causality. And it's like, well, it's defined as not being linked spatially, causally. So it's independent of that. And it would lead to different physical outcomes rather than violate causality under their proper interpretation. So, and we'll get into some of that as we continue here. So relativity, the simultaneity. So this is from 1922 when Einstein's going over the twin paradox, and he's saying that there needs to be reciprocity in the frames of the moving clock. So he's describing moving clocks in the system above, and he says the two consequences which hold mutatis mutandis, which is just a fancy Latin way of saying vice versa for the frames, the one in motion with respect to the one that's stationary. For every system, form the physical content free from conviction of the Lorentz transformation. So, got to hit up your boy Lorentz, apply his transformations, and show that their consequences which hold vice versa right? The change in length and time. All right. So again, he kind of starts to kind of give you an example of the train. I haven't uh, the train scenario with the relativity of simultaneity. Let me show you that first before I read the example here. But to make the distinction clear here, right? Einstein saying that if you're on a train, you have an observer here that intersects with a stationary observer, and you have lightning strikes that occur at A and B because the observer on the train is moving towards B and the speed of light is constant, is going to perceive this event occurring first. And remember, the sequence of events has to be physically meaningful and valid, um, not just hypothetical, right? Otherwise, it's just absolute, and we're not deviating from classical physics, and everything we said to answer Michelson-Morley would just be a role play. So, um, so what we need to be able to show here is that through transformation, we can make the stationary observer see the simultaneous event as not simultaneous, and the train observer see the event as simultaneous. Now, you can do this through Lorentz transformation. But when you get into accounting for the timing of the propagation of the information to the midpoint, that's where a lot of people get lost in the analysis and conclude that because they're accounting for the timing difference of the propagation to the midpoint, that that physical agreement of the simultaneous event is okay, that it's that both would agree on the outcome. So in the scenario where you could devise, different ways where a bomb would go off in one frame versus the other frame, dependent on a simultaneous event occurring and how that information is received on the train, you would have to say that in one frame, in the train frame, the event wouldn't be simultaneous, so the train doesn't detonate, where the stationary observer sees the train detonate. And that sounds wild, right? That's makes no sense. But that is what is explicitly mandated because there's no absolute simultaneity. There can't be the sequence of events spatially separated events, which is independent of the time coordinates of these lads here, right? If you have to make the sequence of events capitulate to the stationary observer, then the stationary observer's frame is distinguishable from the frame moving at a uniform constant velocity, and the whole theory is not true. So this is extremely important to understand that it is, mandatory for this outcome to occur. Otherwise, you can't have the mutatis mutandis, right? You can't have the reciprocity between the two. If they both agree on the outcome, what are we transforming? Right? That's not that's not the meaningful conclusion to the interpretation. So in the example given to the side here, so instead of having a train and lighting strikes, suppose you have a balance beam and we have balls that are going to fall. If the balls hit the balance beam at the same time, the balance beam won't deviate and the balls will just bounce up and down a couple times and then they'll remain stationary on the balance beam. Let's like idealize hypothetical, right? Now, in the scenario where the moving observer intersects with the stationary observer, he's going to see the B ball falling first. He's going to so he predicts that following his sequence of events, if it's valid, the ball would hit the balance beam, it would deviate, and then let's say there's dominoes on the ground here, and when these balls fall on the ground, they're going to hit dominoes, and it's going to, the dominoes are going to knock over another chain of dominoes, and it's going to trigger another chain of events, right? So this entirely separate timeline is going to occur for this moving observer versus the stationary observer. And and what's meant by the reciprocity and the outcomes for the simultaneous event is that, right? Otherwise, we're not saying anything new about physics. So Einstein says here, he gives his train example, and goes on to talk, and he'll go on and later reference how, this was proven, right? It's a thought experiment, guys. This has never been physically manifested, but this is what he proposed to everyone, for physical meaningfulness for his equations to apply to give an explanation to Michelson-Morley and stuff like that. So reading here at the bottom,
He says events which are simultaneous. This is just the train reiteration, what I already read and laid out about how they're not going to be simultaneous in one frame and not the other. So he goes on to say, events which are simultaneous with the reference frame to the embankment are not simultaneous with respect to the train, and vice versa. Relativity of simultaneity. Okay, so that's what we're okay. Makes sense so far. Every reference body coordinate system has its own particular time. Unless we are told the reference body to which the statement of time refers, it has no meaning in the statement of time of the event. So hopefully it should be clear by now, as he's proposed the theory and some time has went on about the distinctions being made from his 1905 paper. And then he goes on to say in 1940 that he's talking about Maxwell's equations and how they, following the inertial frames, how they're defined in his theory, all check out. So this leads to the result that the Lorentz transformation applied as space-time coordinates must govern the transition from one inertial system to another. In the content of special relativity, the theory can be accordingly summarized in one sentence. All natural laws must be conditioned that they are covariant with respect to Lorentz transformation. And we'll go over what that means here in a second. From this, it follows that the simultaneity of two distant events is not an invariant concept, and that the dimensions of a rigid body and the speed of a clock can change depending on their state of motion. Extremely important. Now, remember what he said in his 1905 paper. For events that are close approximation, like the train that he goes on to give, requires further mathematical abstraction. No one's ever shown the mathematical abstraction. A lot of people just misinterpret the sequence of events and having them line up by accounting for the timing difference, which doesn't lead to the proper reciprocity that needs to be shown for the simultaneous event that is is not an invariant concept. Okay. So an invariant concept, what this means, what he's talking about with covariance, he's talking about invariant transformations for the speed of light with respect to inertial frames. And inertial frames are going to be where the measurements are taking place, or with respect to the measurement and the phenomenon in question. So um, what you could do, like what you'll see for we'll kind of gets into the Sagnac stuff later, but it's just important, which we're going to cover here in a bit, but I don't want to get too far ahead of myself. It's just important to note here that we're talking about where the measurements are made with respect to the emitter or the phenomenon, the thing that's emitting the light that we're doing the analysis with. So anyway, he goes on to say here, once it was shown that simultaneity was relative and depended on the reference frame, every other possibility of retaining action at distance with the foundation of physics disappeared since, since the concept proposed an absolute character of simultaneity. Okay, so remember, simultaneity is, I'm sorry to be repetitive, but the distinction here is extremely important because it's even noted, in the early 2000s from a study done, from a blind study from students at different levels of academia, postgrad, undergrad, all these different levels of it, where they do the relativistic equations, they do the transformations, but they don't have the proper understanding of what relativity of simultaneity means and what they calculated. And when they get into different paradoxes, they're unable to answer them because um, their mindset is rectifying, or their mind is having trouble rectifying the necessity of of physically different outcomes between the frames for simultaneous events, because in reality we all know it's an apparent effect and it's hard to let go of that. So that's what the students are having trouble with, is letting go of that. Okay. So in the 1920s or so, Lorentz writes to Einstein, and because his original theory and framework, you can do a summation of his transformation and determine the proper sequence of events. Whereas Einstein saying that there's no absolute simultaneity, right? You can't, even though you can mathematically do this, like just don't, right? Don't interpret it that way as meaningful or whatever, right? So Lorentz writes Einstein and he says, hey, given the coordinate system u and u prime and in non-spatially separated, I'm sorry, given spatially separated events that are not causally linked, um, we know that we kind of know that there's a preferred sequence of events, and that's the simultaneity that you're proposing hasn't been manifested. Do you think there's like a universal spirit or like a God that permeates the entire system under consideration that preserves the order of events so we can immediately distinguish one of the systems of U and U prime, etc., over the others for the to resolve this? And Einstein never wrote him back. He was like, because there's no way to rectify this, and it's literally built in the original framework anyway. And so Einstein's like just philosophically like, no, it doesn't mean anything. So anyway, we're referencing here now from 2002 the challenge of changing deeply held student beliefs about relativity of simultaneity. And this was the blind survey study that I was referencing, where they were surveying different levels of academia. Your hot mic in, mister. Shout out to the young lads though that you got with you. So anyway, the introduction here. So anyway, they go on to say that um yeah, we found that the students leave the standard introductory course or the advanced undergraduate courses on relativity with some fundamentally incorrect beliefs about the definition of time of an event and the construction of a reference frame. So that's why I went into such detail earlier on, where these equations apply, where we're putting them. Is it an arbitrary place, or is it where the instrument measurement took place? Why it's important to define them between the two. And then it goes on to say that yet many of these same students also have a deeply held underlying belief system that simultaneity is absolute, and that when the signal time is accounted for, all observers in the reference frames agree on the time and the order of any two events. But many students fail to recognize one of the profound implications of special relativity for our understanding of the nature of time. So, the correct way to interpret this is that there's relativity of simultaneity. There's no absolute simultaneity for what they're proposing. And this, is hard for them to accept because, like many people have put forward to answer this paradox created by different physical outcomes, don't actually um they're not even they're not fundamentally even answering it correctly in the paradigm, right? The solution they're giving is because of their mistaken belief in absolute simultaneity according to this study. So the units of measurement that we looked at earlier, length, mass, and time being the fundamentals for everything, right? When we gamma factor them for the change in time, or for the coordinates, or for those time coordinates and distance coordinates and mass values, they're going to be a factor of the velocity squared over c squared. And this covariant relationship means that time and space in between the transformations between the observers, where the instrumentation is measured, you can show that where one frame will be contracted, the other frame will not be contracted. It'll have the actual length and time, right? So that's what they're showing there. So the relativistic units, so time, distance, and length are all gamma factored. And then on covariance, which is an important relationship, which earlier when they established the equations and the variables to use for force and momentum and all that stuff, and like where they apply. The rules were, symmetry in the equation. You have to have dimensionally consistent units, meaning like if you're using kilograms, you can't be, um, you can't change that to like meters or something, right? You have to, it has to be dimensionally consistent. So, um, with that kind of building on that for the transformations, we're like, okay, so if time and space change as a function of velocity, we have to be able to show that time and space, when we transform, these coordinates have to transform together for symmetry. So that's why space and time, that's why they call it space-time symmetry, or space-time as one word, right? They're supposed to be merged together. Um, so anyway, under transformation, they're supposed to be the same. And all natural laws are supposed to be covariant under Lorentz transformation. So earlier, when we went over the dynamic analysis, just doing the uh, classic Newtonian transformations, we showed that the energy predicted in the frames wasn't equivalent, but like somehow, you know, when we introduce Lorentz transformations, these are supposed to work itself out and be consistent to be meaningful. So this covariant relationship is how they uh, interpret the meaningfulness of their calculation. So some people will be like, "Well, you've never been to this reference frame. How do you know that that the laws of physics apply there in this way?" Because they calculated it through a transformation, and the transformation was symmetrical, and they followed the rules for the transformation, and they got the corresponding outcome. And they could show reciprocity in the frames. So they have determined from that is the correct and valid way to interpret it. That's how they did it. But there are rules for that have to be satisfied, which are often overlooked in the mainstream or bent. You know, so we'll get into some of those as we continue. And let's see. So in the other introduction for the relativistic framework is energy and mass become interchangeable. So energy E equals mc squared becomes an important concept for them. So that's how they're going to get mass to change as a function of velocity. Uh, okay, so I think I covered everything I need to from here. Okay. So yeah, this was just on the what Einstein said earlier about the from this page right here. Okay. So when we get into covariance, we're looking at Einstein was satisfying this algebraically, where Minkowski gets into like a geometric property situation. So we've all heard of like Minkowski space-time. I'll show you guys the diagram here in a second. But with the beauty of using the geometric transformation that Minkowski put forward is that anything that occurs within the light cone, meaning not going faster than the speed of light, will automatically be covariant under transformation. So you don't have to do the rigorous algebraic transformations that Einstein was doing. So that's kind of the difference between the two, but still satisfying the same conditionary aspect of the mathematics to interpret it as physically meaningful to get the same results. So here we're looking at different aspects of the same thing. So the Lorentz transformation in the middle here from Einstein showing the change in the time, change in the distance as the gamma factor being a function of velocity squared over c squared. And then when you plot that out, what it would look like, you would get because this is a quadratic equation, you get a hyperbolic change in the different times between the stationary and the moving observer. So t prime here and x prime are going to be defined as our proper time, coordinate time, and coordinate distance. The unchanged distance and time that the proper time is going to be relative to, that the change is going to be occurring in, is going to be shown here by this hyperbolic curvature here. So as you go faster and faster, you would get more, as you approach the speed of light, you would get more contracted, more dilated. You would get more curvature in this graph. Now, if you took this graph and flipped it 360 degrees and made infinitesimal sections of it, you would get a cone out of it. You would get this right here. So that's kind of what Minkowski did with this light cone situation to describe space-like and time-like events. Following, as long as nothing goes faster than the speed of light, you're good to go. So anything that occurs in this cone geometrically it satisfies covariance. Then when we get into the field equations for the general theory, proposed in 1915, one second, I'm going to get some water here.
I saw him once in the sunroom when my daughter's family came.
All right, so we got the so covariance in the field equation. So in 1915, he put together the general theory. So there was following Michelson-Morley with proposing link contraction and time dilation for frames in uniform constant velocity. They needed a way to describe gravitation and acceleration and really remove this idea of an absolute frame and kind of fully get like a framework out there that would fully commit to the replacement of absolute. So how do we get there? We need a vehicle to do it. And this is going to be how we're going to do it through the general theory. So in the general theory, we're switching from regular algebra to absolute differential calculus. What that means is we're going to take a structure defined as a manifold, and we're going to take little sections of that manifold. And as long as we take sections of the manifold, we're satisfying, we're like, as long as we're like operating within the boundary conditions of this manifold, so to speak, we're good to go. And we can do that by taking infinitesimal sections of the manifold and then arbitrarily defining points in the manifold that will change, that will be, that will describe the amount of curvature in between them in the manifold. And the manifold, of course, will be space-time. Now, we've all seen the example where they have a bowling ball and they have it at the center of like a sheet, and it's bending the sheet, and they roll balls out, and they're like, look how it's following the curvature. So that's obviously not meant to be like a physical representation of the bending of space-time. That's just kind of to put like the conception of how they want you to think about it in there. And it makes it easier to kind of digest. But what they're really talking about is satisfying mathematical conditions of a complete abstraction to facilitate the concept of covariance, which is giving them their physical meaningfulness. So anyway, we'll kind of come back to what that means as we go forward. So looking at the tensors up here up at the top now that describe this manifold, we're looking at going right to left here, we're looking at T, mu, nu, which is the mass, energy, and momentum tensors. So to describe the amount of space-time curvature, which is going to be on the right hand or the left-hand side of the equation, defined by G mu nu minus lambda G mu nu, big G minus little g over there, which I'll get into what this is in a second. But anyway, before we can describe how much this manifold is going to curve, we need to know how much mass, energy, and momentum to conserve into a gravitational field to cause the bending in the first place. So to get out of an absolute frame being the Earth, remember Newton said that it was probably in the solar system at the barycenter. Mach said that it was probably with respect to the Earth and the mass distribution of the universe. But we're getting away from these concepts of absoluteness, even for acceleration and rotation. And to do that, we need to say that there's no absolute frame, there's no rigid coordinate system that we can use arbitrarily, right? To get that off of the table, we have to know the mass of the universe and the distribution, so we can describe the energy distribution of it, so we can describe space-time curvature for that manifold, so that we can take smaller sections of it to do, like, we can take little derivatives of the curvature, so we can assign points in it to it to describe how much curvature is going on in that infinitesimal section of space-time, which is a lot to kind of go through and process, but that's the backbone of why these equations are necessary. And we kind of talk about, what will the next theory be? What are they going to replace it with? There's nothing to replace it with. There's absolute and there is not absolute. So this is already the non-absolute theory has already led to insane contradictions when applied to cosmology explicitly. So Newton's equations, as defined, or to describe the dynamics of the sky, the motion of the bodies. In particular, like to give a quick example, there was a perihelion precession of Mercury that was observed, and if gravity is the causal mechanism as defined by mass attracting mass to produce these effects that we see in the sky, when you're perihelion, you're locked into your planet orbit. You can't have a perturbation in your orbital plane. So the fact that there was, and they couldn't account for it by adding up the masses of the other planets and using like a gravitational tug of war, this was like a huge problem, because it means that mass attracting mass as defined by Newtonian dynamics applied to the sky isn't meaningful. So this was like, how are we going to fix this? So moving forward, they had to come up with this scenario to, be the opposite of absolute. So there's not going to be another thing to come around, because nothing is what's already been like to get us here, to get people to accept this already. Already took so much effort. They're not going to replace this. There's nothing to replace it with, because the alternative is to acknowledge the measurements of Michelson-Morley on the face of it, which imply that the Earth is either moving extremely slow compared to what they needed it to be to substantiate their cosmology, or the Earth is stationary with respect to a dynamic ether wind. In either case, they can't have that be a tenable position that's on the table. So this is what they've done to abstract everything and make us believe that this is where we're at in physics. And then, like, because it's dressed up in these tensors, and it's requires a high level of calculus to understand, a specialized field of it to grasp. It's kind of like wrapped up in this garb of like, you don't get to like understand it or critique it even, but without being able to even solve it, even though, like, fundamentally just going over the history of what they've done and what they're laying out and the importance of this covariant relationship that they're trying to establish, it's very obvious, what's being done here. So as time and space change as a function of velocity in the special theory, what he's introducing here is that for rotation and gravitational fields, there's going to be a same effect of link contraction and time dilation that will cause the same thing. Like the effects would be the same, in that inertial, like, pseudo forces would arise as due to effects of space-time curvature. So yeah, he talks about here at the beginning, he says, or I'll just read from the end here. He says, just as the special theory is based on the postulates that all equations have to be covariant relative to linear orthogonal transformations, meaning the x-axis and the time axis, which is always perpendicular to the x-axis, have to be in alignment to each other for the transformation to be successful. Otherwise, you have to do a rapidity correction, which is just like the angle deviation. Not going to get into all that, but it just means it sounds fancy, but it just means that both coordinates have to be lined up to each other at the same spots. So the theory developed here rests on the postulates of covariance of all systems of equations relative to the transformations of the substitution determinant 1. And so remember, there's no absolute time or space, but we're going to use the mass distribution of the universe to impose a curvature manifold, and we're going to use that as like everything is going to be relative to that. It not absolute space, guys, but to this. So he says, nobody who really grasped it can escape its charm because of the significance. Because it signifies a real triumph on the general differential calculus as founded by Gauss, Riemann, Christoph, Ricci, and Levi Civita. So the founders of absolute differential calculuses and the boys who pioneered manifold and curvature mathematics within that structure. He's like, we can definitely make use of this, boys. So real quick before we go on, obviously satisfying conservation laws is a big part of physics. It's a big part of the mathematics that describes the physics. And so if you can't just satisfy the conservation laws, then you're in for a real problem here. So earlier we talked about how mass changes as a function of velocity or energy. So Einstein had this issue satisfying conservation laws, making relativistic mass covariant with rest mass. And he wrote Lincoln Barnett in 1984 in German. And he says, the translated passage says, "It is not good to introduce the concept of mass, big M equals m over 1 minus v squared over c squared of the moving body for which no clear definition can be given. It is much better to introduce no other mass concept other than rest mass, the little m. Instead of introducing m, it is better to introduce an expression for how momentum and energy of a body is in motion." So to kind of give like a little history recap, there was a problem with the T mu nu tensor over here in the geometric structure of absolute differential calculus, and how the conservation laws to define the gravitational field to do this weren't being satisfied. So this was like a rest or an issue that Einstein was coming back to try and fix over the years, and he could never quite satisfy it. Several other tensors have been introduced that are said to have been, derived properly to satisfy the conditions of covariance, but analysis have been done on those to show that they suffer from the same issue. But that's kind of like a bit above the my ability to give a coherent analysis on. So we'll skip past that and go to like a simpler version of what's going on here. So these equations, right, there's only 3 solutions to them. And the way that you solve absolute differential calculus equations, you need input and boundary conditions. So the boundary conditions, we're going to have to know the mass distribution and energy of the universe so that we can know how much that's going to curve our manifold. So those are the predicaments that we're in. So you can make certain assumptions about the mass in the universe to describe the curvature in the system. So for example, when you get into the Schwarzschild system, it assumes no mass in the universe. Oh, they also assume different things about, like, is the system eternal? Is it finite? Did it, when did it start? Does it have a beginning? So all of these things are defined in your metrics to determine the solutions. But anyway, there's only 3 valid solutions. So they all have different interpretations of how they describe the universe and the origins of the universe in those equations, which makes them contradictory to how people apply them later to tell stories about black holes and Big Bang universes, etc. So to kind of move on from that, so this means that they're non-linear. So remember how in Newtonian, you could add mass together with the 5 pounds and the 15 pounds and that kind of stuff. And you could solve different equations and you could add them together. You could do velocity addition, stuff like that. So in these, each differential equation solution, you have to calculate it, under specific parameters. Otherwise, it's going to change the outcome, and you can't add them together because there's no absolute thing. The parameters were already defined when you started the calculation. So if you have an outcome that describes one universe that you say, cosmologically speaking, okay, we have a Big Bang universe. We come from this explosion out of nothing. There was this period of mass and matter and different states of cooling and this thermal radiation that's now the background, CMB and all this stuff. Where did it come from? How did it distribute homogeneously? All has to be described with specific parameters in the T mu nu part of the equation. So this will be significant when we get into black holes, because that describes a universe that's empty and contradicts these things, and it has different mass values. So this assumes the total finite mass in the system when you're applying it to something like to explain the Big Bang theory, when you're using the FLRW metrics versus like the Schwarzschild metrics or Kerr metrics to describe black holes. So a man named Stephen Crothers, who was getting his PhD in general relativity, he was doing a mathematical analysis on it, and he found a bunch of contradictions. And one of the ones that he found was in relation to that tensor and how it doesn't dimensionally satisfy the conservation laws with that issue that Einstein was having with the relativistic mass. But a simpler one that he found that's a little easier to understand is that the value given for the radius derived in black holes from the Schwarzschild metric is a coordinate label that they're using for a specific point in space-time. It has no dimensional properties. It's not an actual thing. It's just an arbitrary point, because when you're using these tensors to describe space-time curvature and like events that are occurring in them, after you've got your section of your manifold, you need to describe, what's there, right? So you put a little dot at this coordinate, and then you put a little dot in this coordinate over here, and then you can draw lines between them to establish the angles and the curvature that's occurring between them with respect to the space-time manifold based on whatever properties that you have assigned to them from the conservation laws. So they don't have like dimensional properties. They're like they're placeholders to where you can have the thing be like relative to in the coordinate system. So that's really important, because what Crothers says here is the way that they say that, okay, the way that they're looking at it as a dimension, and when they apply it as a radius, they're like, oh my God, the gravitational potential at this radius exceeds the speed of light. That means that if the speed of light entered in this area of this radius, it wouldn't be able to escape. Where would it go? And then they get into like the singularity and all this stuff for fun. But the main takeaway here is that they've extrapolated this from a part of the mathematics that has no physically meaningful dimension, and they're attributing a radius to it to describe how much gravitational potential would be at that radius. So in order to describe the radius, Crothers says you would have to take an integral between the two coordinate labels that you're using, not the coordinate label itself, because you're going to get different distance values for your r based off of that. And when you do it the proper way, when you do it between the two coordinate labels, the r value that you get doesn't lead to a black hole. It leads to a gravitational potential increase, obviously, but it doesn't break the metric anymore. So they've imposed a scenario where they've broken the metric and then told a story about how this implies that, that there's a black hole out there. So when they get into things like Hawking radiation and the LIGO and all these things where they've confirmed these black holes, well, these are derived from a metric that describes an entirely different universe from the one that they try to assert cosmological dominance over with the Big Bang Theory. They're contradictory, and you can't add the masses of the black holes or anything that they produce to the Big Bang metrics. So they come up with this story where they're like, oh, well, you know what? It's actually, if you added them together, it would be insignificant in the overall thing. It's like, no, you're using nonlinear field equations linearly. Like, you guys, somebody has to step up and say something. So that's what Crothers was doing, and he got expelled from his PhD program. They wouldn't let him continue. He threw a wrench in the whole thing and ended up getting expelled. And then he gets into a back and forth with the director of the International Gravitation and General Relativity Theory Committee, where these people are in charge of interpreting the field equations and like the solutions to them and how they're going to be taught to, across different universities. And so the critiques that, like the thing that was like a big red flag for me, because like the math is obviously intense, right? But the criticisms that Crothers was getting from the faculty that, were supposed to be able to understand this, they were changing his work, adding their own stuff to it. And they were going, look, when I changed here isn't correct. This modification I made now invalidates your equations. And he was like, "Why are you changing my work and then dispelling it under the grounds that that was something that I asserted in it? It doesn't make any sense. Why are you doing that?" And so that started with the faculty at the University of New South Wales, where his superior that he was supposed to be getting his sponsorship for his PhD for or whatever was was doing that to him, and nobody on the committee could ever address that. Nobody could ever explain why they was doing that, and the guy at the gravitational committee did the same exact thing. So there's no actual refutation to it. And then when he started calling out other big names in cosmology that are doing this, what they started doing, they started saying, "Well, yeah, we know that it's not the radius. We know that it's not." And then on their websites, they'll use it as the radius. So like they're in this weird situation where when some of them get called out on it, they're like, "Oh yeah, it's not the radius," but then like it obviously it has to be used at that value, otherwise it doesn't produce the correct effect. So Crothers gives this anecdote here at the end of his thing. It says a non-simple proof that they're wrong about their mathematical theories of covariance and Einstein's field equations and all that. It says it can be easily proven that a black hole and the Big Bang contradict one another, and so they are mutually exclusive. All alleged black hole solutions to Einstein's field equations pertain a universe that are spatially infinite, are eternal, contain only one mass, are not expanding, and are asymptotically flat or are asymptotically curved. But the alleged Big Bang universes are spatially finite or spatially infinite, or have a finite age, or contain radiation in many masses, including multiple black holes, some of which are primordial, or they're expanding, or they're not asymptotically anything. The black hole universes and Big Bang universes contradict one another. They are mutually exclusive so that they cannot coexist. There it is therefore not possible for a black hole to be present in a Big Bang universe or even in any other black hole universe, and likewise, it is not possible for a Big Bang universe to be present in a black hole universe or any other Big Bang universe. Nonetheless, the astrophysical magicians superpose black holes in the Big Bang universe, notwithstanding that the incompatibility by their very definitions and the principle of superposition does not hold in general relativity. So the superposition would be, adding the masses together, adding the solutions from the field equations together, making them linear, but they're nonlinear. So this doesn't lead to physically meaningful outcomes. Of modern physics is simply manufactured in a way, and so it bears no relation to the actual universe. So pretty damning stuff. And then to kind of end on that, we have reference frames describing where the measurement is taking place for the Sagnac effect, and for a rotating interferometer, we have an observer at the rim. We have an observer at this on the device here that's in rotation. Now, Einstein defines uniform transitory rotation as a place where his equations apply. And we even have things like Thomas precession to describe it, rotating frames. We have things like rapidity corrections, where we can offset the deviation and the angle at any infinitesimal point in time to set up for the linear orthogonal transformation. So none of the saying that it's not relevant or not an inertial frame, or that it doesn't apply, isn't really relevant, because you can use the equations to describe it. In reality, the observer is fixed here at the rim. The source is fixed here. There's no relative motion between them. The only thing that would be able to measure that would be if you could take a snapshot of a fixed point of this rotation and preserve the path length as this rotates to have a timing difference in the clockwise and counterclockwise speed of light as it traverses its circuit here and then recombines to make the measurement. That would be the only way that you could describe that. And same over here with this configuration, showing that only the top portion moving with the delta L, meaning the effective length here, not the whole section. So only the relative moving portion is moving at a uniform speed, and it's moving with respect to a detector that is stationary, and there's also a configuration where it's moving. And relativity predicts that if these are in uniform relative motion to one another, there should be no fringe shift pattern measured. Yet in either configuration, the fringe is measured directly proportional to the velocity, as shown by the graph here. So when we get into the analysis for relativity to answer this, we can't use the reference frame of the observer here at this fixed point or the one here, because relativity would predict that the speed of light would complete this circuit independent of the motion because there's no absolute frame for this to be relative to. And when we complete the circuit, the speed of light's going to recombine clockwise and counterclockwise and produce no fringe. Same situation here, produces no fringe. So this is the fact that these measurements are made completely contradicts the explanation that's given for Michelson-Morley, because remember, their measurement was 6 to 8 kilometers a second, and length contraction and time dilation are extremely small effects. That's why they had to round the measurement down to 0. They can't even answer the fringe, the fringe pattern that was just over one fringe. They can't even justify that distance with length contraction and time dilation. They have to say that that distance actually doesn't exist. So just kind of like let that soak in, that they're saying that there's no distance display, there's no fringe displacement, even though they were looking at it and measuring it. They're saying there's none. But when we're looking at this one being measured proportional to the velocity in the same way, this isn't supposed to exist in their paradigm. Hell, they can't even explain the rotating one either. This actually went unanswered for years until Paul Langevin or whatever came along and said that using general relativity and using the center of the apparatus, we can invoke a fictitious frame there, and we'll just go ahead and allow it. And it's like, okay, dude. And that still doesn't explain it under the confines of contraction either, though, because remember, this is proportional to the velocity. So we can't have a first order timing difference in the speed of light that's directly proportional to the timing to the timing offset to produce the measurement proportional to the velocity. That doesn't make any sense. It would relativity, if it predicted a measurement, it would be much smaller. So a configuration is given here in 1942, where the source emitter and the recorder are fixed to the lab wall. And there's also a configuration that was done where they had a second recorder that was fixed to the apparatus as well. But we won't cover that for now. We'll just stick to the initial configuration. So what they have here is a source emitter, a laser beam emitter, and a photographic recorder fixed to the lab wall. And it's shooting a laser beam to a beam splitter that's fixed to a stationary disc up here that has 45-degree angled mirrors that go down to another disc that has 45-degree angled mirrors. Now, this bottom disc rotates out from underneath of the top disc. And after it completes its rotation, the 45-degree angle mirrors will align with the 45-degree angled mirrors up at the top, and the light beam will complete its circuit and go back to the lab wall where the source and the emitter are fixed. So not on the rotating platform. Now, these two observers, the stationary lab, wall frame emitter and the recorder, are inertial observers. They're certainly defined as inertial observers in relativity theory. So they predict that the speed of light isn't going to measure a change, and yet the first order timing difference is measured, again, proportional to the velocity of the rotating platform. They measured the same thing in the classical theory using the classic equation, which we went over earlier in Michelson-Morley, which makes it's essentially the same as the correction for the Sagnac effect. Predicts the full fringe theory, so they're good to go. Predicts the full fringe, so they're good to go. Relativity is off by a factor of 10 using the proper reference frames. And Paul Langevin again goes on to comment and say, well, we have to use a preferred frame because we're dealing with rotation and gravitation. And that's really the only way that it makes sense to do it in the general theory. So he just kind of chalked this up to a big L and said we have to use this preferred frame. So the preferred frame, remember the instrumentation isn't at the center of this device. So when they put an observer at the center here with coordinates arbitrarily, they say arbitrarily, but there's no other way to answer this. They're breaking the first postulates that we went over that were on page 1 of Einstein's theory. This has to be answered on the frame in which it was, where the instrumentation is, where the observational observer is. And it leads to the wrong prediction. So the general and the special theory both have no explanation for this first order timing difference. And here we have PhD Blitz, who runs a YouTube channel and TikTok, modern relativist and quantum electrodynamics guy, tried to derive the Sagnac effect. And here he starts with a rotating cylinder coordinate system from Minkowski. So he's got the coordinates for a space-time for a cylinder, and he does a transformation to a rectangular coordinate system, just taking all the time coordinates from it. Nothing fancy here. And then for the equation to describe the rotation of the coordinate system with respect to the midpoint and then placing an observer at the rim of R, we have C times omega plus or minus 1, which is describing C plus or minus V clockwise or counterclockwise with respect to the center axis of rotation. And his comment on this was that the reference for, that a coordinate system rotation is the answer here. And as we can see, there's no Lorentz transformation here. This is a way to describe the classical derivation for C plus or minus V. This explanation does nothing to offer a relativistic explanation or derivation for the Sagnac effect. It's impossible to derive the Sagnac effect under relativity. Relativity predicts that inertial observers measure the speed of light being the same. The Sagnac effect measures the timing difference with the speed of light proportional to the velocity of the observers. They're literally contradictory to one another. And so one can't be a prediction of the other, right? So the solutions that they propose violate space-time symmetry. They'll do asymmetrical transformations where they'll only do the time coordinate, and they'll assume so they're assuming absolute distance, right? They can't actually answer this using the proper relativistic derivation. So again, just kind of showing what that was there. And I already went over what was wrong there, but primarily, like on the face of it, no Lorentz transformation, not even a little Lorentzi. So conclusions here. What are we concluding from all this? That when we look at GPS, it is a system that derives distances based off of timing intervals, timing and positions of when signals were sent and when they were received to determine distances. And this is all based off of GPS time. So it's based off of a singular cohesive timeline. So let's assume that relativity is true and, there's no absolute time, but through corrections and a lot of ingenuity, we've established GPS time, which is a universal timeline that everything can be relative to, that we can use, that we can synchronize all our devices to, and maintain a consistent timeline. Well, if the effects of relativity are true, we're still going to have to deal with them within our man-made timeline. So if the example that Einstein gave, being on a train and having moving and stationary observers, well, that effect occurs every day between, all over the world with GPS and DGPS signals being sent at the same time to observers that are stationary and moving relative to one another. And so if relativity of simultaneity were true, then the simultaneous event of when the signals are sent to the observers that are in motion relative to one another
would actually be sent at a different time, and you would have to come up with some sort of correction to account for relativity of simultaneity. Now, no correction has ever been needed. They actually don't do Lorentz transformations in GPS. They use Galilean transformations from the ECI and ECEF in the Navstar documentations and all the ICDs that I've read. They're all dictated by classical equations. Looking at an engineering overview from, what was it, 1998? They were saying that basically the relativistic effects predicted by general and special relativity cancel each other out, and we can just kind of answer everything using the classical stuff. And in 2004, when Neil Ashby went on a 20-year public tour proclaiming that that the Sagnac effect measured in GPS is one, proof of relativity, and two, well, actually that was like just his big main thing. But anyway, he was saying that that was proof of relativity theory, but when you look at the transformations that he was using to describe everything, he was just using Galilean transformations, so absolute time transformations between the reference frames, invalidating the hypothesis that Lorentz physics exist in GPS. Similar to what the engineering overview stated, because at the end of it, there was reference from Carroll Alley, who did some experiments with atomic clocks, saying that he had confirmed relativistic effects in atomic clocks, and now we're going to have to account for these things. And then so at the end of the overview, he's like, "Hey, we don't have special origin or relativity accounted for yet, and I really think we should include it. And we don't have relativity of simultaneity in here either. Let me know if you guys ever want to include those things. That'd be super cool." What are our conclusions? Time and space are absolute. Creating time and space for stories about mass distribution of the universe to satisfy tensor calculus is physically meaningless. We have first order measurements of at non-relativistic speeds showing that the speed of light measures linear motion. We have, which in scenarios where it predicts the opposite, we have measurements that contradict the proposal of relativity of simultaneity being able to explain the desynchronization of the interferometer as it rotates. We have GPS timelines working off of absolute time, but no relativistic physics included. So even with the simple first order V over C, not being able to explain without invoking mass distribution or a preferred frame, really solidifies that the relativistic philosophy and position isn't valid, especially when it's applied to cosmology. The laws of mechanics, is not singular, right? And they're only satisfied with respect to the lab frame, as we showed earlier when we went over the different scenarios with the bike, the juggler, and the train, hiker, and the bucket of rotating water. So shout out to Cassander, who proposed the absolute lab frame with a flexible ether, meaning the velocity measurements that are made with interferometer, whether it be a right angle interferometer or a closed loop, are measuring a dynamic ether wind with respect to a stationary Earth, meaning the ether is in motion and the Earth is stationary. So, are there any questions, comments, or concerns, anyone? Thank you all for attending. I hope it wasn't bad.
There's a lot of information.
It was all the information. It was the complete history and recap of physics and where we started, where everything was built upon, and where and why things had to deviate, and the meaningfulness of what we're jumping into when they're saying, "Hey, we're going to introduce relativity as the solution here." Like, what does that mean exactly here? What are y'all calculating under the hood?
Exactly. Yep.
It was really unfair of you to do that, Alan, given the last night's knockout punch was already given.
Yeah,
Hey, Alan, can you go like a few slides back?
absolutely. Say when.
Okay, wait, next one. Right there. Can you no, the next one.
This one?
The one right after that, my bad. Yeah, that one. Can you describe what the S was in that chart
Yeah.
and the what you're trying
Yes.
to circle right there in red?
Yeah, absolutely. So the red circles were supposed to be the detector and the emitter here, but when I resized it, it kind of offset it. So I wasn't able to correct it, but these are just supposed to put a circle right here around the detector and then the emitter. And the big S here is the area that light travels in this apparatus. So when they do the derivation for it, for their equation, they use, what is it? It's like 2 times the area. And when they do area, that would just be like they're describing this path length here. So when Wang did his experiment, instead of using area, he just uses the length of the cord for the interferometer. So it's just the same thing, but just like a different way to describe the same thing. What Wang showed is that, oops, accidentally closed that. What Wang showed was that it doesn't matter what you use to derive it; they're equivalent. You can use the area or the length, and they both make the same prediction.
Yeah, I got a question real quick.
Wait, did you not hear my last question? I might have been muted.
I didn't hear it.
Oh, I'm sorry.
No.
I'm sorry if
Yeah.
I was muted. I was asking.
No, go
I was
ahead.
just asking. Sorry. I was just trying to ask about like some of the math that he had to learn for this presentation and like how has that been learning all this math and like, do you ever do your own numbers? Like that's really cool.
No, dude, I get all mine from Bennett.
He's the
But no,
math guy.
yeah. So what we're looking at here, like for the math stuff, right? This is just, oops, let's go back to what we're looking at here. So to start it off, it's just like we start with the basic algebra stuff. So like the equations for Newton are pretty simple, right? It's just mass velocity squared over r. That'll tell you how much force is going to be predicted, and so that'll tell you how much this is going to curve. That's pretty simple and straightforward. And then it builds on that, where it's like, okay, so how do you predict how much force there is for acceleration? Well, it's mass acceleration. Okay. So when we're looking at the difference between the two frames, when one's not in motion, predicts a zero value, predicts no force, makes the wrong prediction to apply force where there isn't one. Okay. Seems pretty straightforward so far. And then when we get into this situation, it's just the same thing, but instead of writing out the numbers, you just write it out in variables. So it's the comparison, like when you're looking at it with like E lab and E ball. So we're describing the frames here, the energy in the lab, energy in the ball frame, and then 1/2 times the mass times the velocity squared is the what was that? That is the much energy and momentum it's going to produce. And so all of that is just, I mean, that's, you can plug in the values or whatever, but like
Dude, that's awesome.
the meaningful part is just kind of understanding what they're describing, like what it's going to give, like the output, right? So this is going to give an output that's relative to the summation of the velocity of the overall system, whereas the other equation is only going to give an analysis that's like missing a component of it, so it's not going to give the correct prediction for the energy. So when you look at those parts of it, it's pretty straightforward. And then when you get into the transformation stuff, that's just like you would have like the stationary frame where all the values would be, actually a good way to look at it would be through this one. So all the values in the starting would be 0. So there's going to be no change. So your time coordinates 0, your distance 0, no changes here. And then the rest of it would just be plotted out by, this is just the velocity. So how much this is going to change is going to be a function of how fast it's going. So like all you need to do to understand what they're talking about is just like how they relate to what they're describing, right? It's like a really easy way to get your foot in the door to understand it.
My last question, what do you think that Einstein would respond to your presentation if he watched it with an open mind?
Dude, he would say, "Thanks for correctly interpreting my the philosophy behind what I put forward." And it's really sad to see people invoke fictitious frames and then say that they're using my theory correctly, even though on the first page I left explicit instructions on how it deviates.
Awesome. Good presentation.
Thanks.
50, you said you had a question? Or not? You're muted if you don't know that.
Yeah,
Moving on.
50, are you at your mic? Because you can ask your question now. Yeah, I guess he's not there. Move it along.
The 50-50 chance he's not there.
Yeah,
All
it's
G, all G. Well, if there's any questions, or if
Well,
anyone else has any questions.
I think the last part was what you said was really important, because a lot of times they're going to say, well, despite what you said over here, really good debunks about this theories have been tested with muon decay, etc. But I think what you said with Bennett of how these phenomenons can be explained by setting instruments in motion. It's the mechanical effects of setting instruments in motion relative to flexible ether. That's important because now you could explain a delay between clock synchronization with biological GPS and muon decay. Do you think any pushback? What possible pushbacks might you see if you generate that alternative explanation for these phenomenon?
So none. It really takes it away because the analysis of muons on the face of it is invalid when you get into stuff with. I spoke to someone recently about heavy ion collisions or whatever, in the analysis in that, where he was like, "Well, with respect to the other ion particles or whatever, they show reciprocity and link contraction and time dilation, but what can never be shown in the analysis is link contraction and time dilation of the lab frame, like where the instrument was actually made." Right, because in what we're dealing with in their system is we have this phenomenon. Okay, so we got the thing moving, and then we have the measurement. So the reference frames to properly describe this under the relativistic confines for link contraction and time dilation for symmetry would be with respect to the phenomenon in question and the instrument making the measurement. And they don't do that. They talk about reciprocity in the phenomenon, and it's like, that doesn't, what does that even mean? That's not, you need to show me the lab frame contracting and dilating, my dude, and no one has ever done that. So when they do the muon analysis from a muon in the atmosphere, they'll say, on the muon's perspective, it would be stationary, and the earth and the atmosphere would be contracting as the earth moves at the speed of the muon to meet it there, right, to show the reciprocal. But what they do in the lab is they'll only do a one-sided time dilation analysis. They never show what it would be with the lab frame, because nobody wants to even attempt uh, link contraction in the lab, because obviously no one's going to argue that you're contracting to the muon at the speed of light, or near the speed of light. So it's not a tenable position even mathematically in their paradigm. So to say that that the muon's decay rate changes as a function of its velocity through ether is a much better explanation, logically, than, hey, you know what? Time and space are disconnected and simultaneous events aren't real, depending on your velocity, of course.
What's your
I
definition
think
of
that's a
ether?
much.
My definition of ether would be so in terms of physical properties, it would be the vacuum permeability and permeativity variables that are given. In terms of, like, what does it do mechanistically? It permeates through all matter, and you can measure the motion of refractive indexes, through ether drag. That was Fresnel's hypothesis, still holds to this day. So It's a permeating medium that all motion is relative to. It has physical properties.
Those physical properties being the permeability of free space as it relates to magnetic and electromagnetic waves.
Yes, sir.
I thought that was like a standard like science like type thing.
No, so in the previous
Permeability of free
conceptualization,
space.
yeah, so in the previous conceptualizations of the ether, they never actually talk about it being like the vacuum properties or anything like that, and they also considered it stationary. But what they did consider, that it was necessary for light, but they just weren't sure on the relationship how. Um, but I would say that following Fresnel's formula, or in what Demjanov measured, where basically these interferometers measure a periodicity throughout the day, that's independent of their configuration. Meaning, if it's a Michelson style or a closed loop, like you would see for a Sagnac, is they'll say like, "Oh, we're measuring Earth rotation." It's like, okay, well, the other one does the same thing too, but you guys are saying that it actually measures nothing. And let's see, kind of, so to take that back to how that relates to the ether. One second, I kind of lost my train of thought with the measurements of the periodicity.
No, you're fine. I was going to also ask you if you
Yeah.
had ever seen the manuals. You were talking about looking at some manuals or something, some technical specs of GPS
Oh, yeah.
standards. Like, do you have the manuals that we can reference, or?
Yes, I do. I'll send you some in chat in 1 second. GPS CD. I have a really good one I want you to take a look at. This one's one of my favorites. Oh, that's not it. Where's my ICDs? Here we go. So I'll get you a couple of these to hold you over. One. See, these are different years. I'm not sure on the years. I just have them marked as 20XXX.
Oh, that's fine.
But but it's over a course of different years, because there's some verbiage change, but they're all kind of the same. They don't show any, like, the math's the same. They changed some of the wording on some of the stuff. There's a real interesting one. Let's see. It's not that one. Sorry, I'm looking for something specific.
No, you're fine.
Oh, I found it. Okay, so it talks about, GPS derives distances based off of a timing difference. And so if you're in motion, if you're, even if it's rotation or uniform transitory motion, doesn't matter. You're still going to get the correct timing. Just, GPS is still going to work for you. It's going to derive the correct distance. So they say that they're getting like a Doppler frequency shift for that, but the speed of light's like, still the same. But remember, timing difference. So anyway, it just says that the GPS receivers typically calculate velocity by measuring the frequency of the Doppler shift in the D-band characters. The velocity accuracy can be scenario dependent on 2 meters per the axis, blah, 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 for the PPS receiver. But again, the degradation of the velocity is classified. So what was found in like the early 2000s-ish, there was these guys, Wolf and Pettit, who went to go get quote unquote raw GPS data from a service center where, like, everything gets where it's all housed or whatever, right? In Colorado. So they go and get their data, and they found that it was already corrected for the Sagnac effect, meaning, like, the speed of light c plus or minus v, and they misinterpreted that as like not a significant correction, and that the speed of light was constant. And it was like, bro, your data set was corrected to show that the speed of light is constant. But anyway,
like, how can you have a Doppler frequency without I mean, they're clearly measuring C plus or minus V, but anyway, they just, I think in the documents here, this was the one that worded it the most straightforward way, and the other ones in later dates, they kind of change it, and they don't talk about it that way. They just show you a diagram, and they're like, look, the output is frequency related.
Interesting. Yeah, that is a little vague for me, I will say. I was hoping they'd be a little bit more clear. I think that would be pretty
Yeah.
damning. But
Yes.
that was a little vague for me.
Yeah, so the implication though, right, it's a timing interval system, right? Because it doesn't derive distances based off of anything else. It uses the range measurement equation. So if there's a Doppler frequency, like the classic Doppler shift, right? Like, so if you take the scenario,
sure.
like say like a submarine in sonar, right? So you would use, instead of the speed of light in a vacuum, you'd use the speed of water, or I'm sorry, you'd use the speed of sound in water, and you would derive distances based off of the timing of that. So the observers wouldn't measure the speed of the wave, at the speed of the wave in the water. They would measure it relative to their velocity. So in the same respect,
Yeah.
they're measuring this, like, this is how GPS works. So it's it's deriving a timing difference, literal same equation, just uses C, the vacuum speed, instead of the speed of sound for waves or in water.
Yeah, if somebody could show that concretely, that would be pretty huge. Like in
Oh,
like
oh, absolutely.
mathematical rigor,
Yeah,
that would be pretty big.
yeah, yeah, I got
And I
you.
wasn't talking about you being vague. I mean the document was a little vague.
Yeah, so the document, like, you can look up range measurement equation. That's like the significant part for the part of the argument here. We have it's well documented. It's, or is my Wang stuff? Re-examining, yeah, right here. So the range measurement equation in GPS is the absolute difference in the time the signal was received and the time that the signal was sent is equal to the speed of light times the signal being transmitted, or I'm sorry, the transmitted signal received minus the transmitted signal sent. So that's how they're deriving distances from it. And from this equation, like, on the face of it, because we're not seeing any C plus or minus V's or anything like that, we're like, okay, there's no change of light speed in here. But when you work this out, the analogy that I just gave you about how the equation is used, um, you actually get it leads you to the wrong interpretation, because when you work out what's being measured, it's deriving the same thing for distances. So it has to derive the distance based off of the timing difference of the velocity of the observer. Otherwise, it wouldn't be accurate.
Can you post that in chat?
Absolutely.
That document?
Absolutely. This is Ruyong Wong in 2000 something here. Get the copy paste for you for the date. And yeah, so he goes on to give the example too about simultaneity and how there's a live example every day with GPS, with trains and people on them and being relative to other observers and stuff, with signals being sent simultaneously. Like, a big part of his, because he never mentions like the ether or anything like that in any of his papers, but his big critiques of the Einstein, like the mainstream Einstein framework, is through how GPS actually works and derives distances and how it's accounting for these velocities. And then of course he did the experimentation where he was measuring linear motion in 2004 with the interferometer.
So is this basically disproving relativity?
Sorry, I'm sorry, say that again.
Is this basically disproving relativity?
Yes. It's showing that the interpretation that is given to us by the relativist is an invalid interpretation. It has no physical meaningfulness. Can it get some predictions? Does it make some predictions? Yes. Does it give some, do certain experimental measurements agree with it? Absolutely. Do you have to violate the framework to get those predictions sometimes? Yes. Does violating the framework render the whole thing completely physically meaningless? Yes. Did they start with the best of intentions? Absolutely. They started off great. It was the philosophical difference in measuring, when they tried to measure Earth's velocity that really put a damper on it.
Yeah, dude. You ever heard of GPS?
Yeah.
I'm looking at this guy, and he's only got the one paper published, which is
I
kind of
think
odd.
I think Alan has Ruhif muted.
Oh, I do actually. Give me 1 second.
Oh yeah, he was talking to you
It's
about how GPS is
Daza.
reliable.
That's
Where-
Daza.
Oh,
Daza.
Daza. Never mind.
Daza.
Oh, didn't hear what I said then.
What's up, Daz? I got you.
Yeah. So you implied a minute ago that all of this renders GPS useless, but we know for a fact that GPS is very precise, very repeatable, and it works, right? Even if there are some questions about how the relativistic.
I never argued that it was useless. I said that it was accurate and accurately derives distances based off of the timing difference in the speed of light, not the constancy of it. And it's accurate
Yeah, but
relative
you
to
did
a
imply
coordinate
before that
system with
it was
corrections.
Mach, right?
Nope, never.
Okay. I must have misinterpreted you then. I apologize.
No worries.
So it's clear that it functions correctly, right? With all of the corrections that are applied, whether you agree with them or not, it actually gives a very good result.
Absolutely.
Very useful, no matter how it was actually created.
Yeah. So even like on a flat Earth or whatever Earth, say you have a specific coordinate system, that's defined by positions of the stars or what have you, and you need to keep everything in the confines of that. But for whatever reason, whether it be Earth rotation or ether wind variation throughout the day, there's fluctuations of the speed of light, and of course you have latitude dependent variance. So you're going to need to come up with ways to have a uniform way to make everything like accurate on that coordinate system. So you would just introduce corrections to it, like whether or not how honest you want to be about the corrections, or like what you present to the public is like, two different things. But essentially, in either case, the accuracy of the system depends on, regular corrections that they do to that GPS timeline. It's actually a really fascinating story how they keep the GPS timeline in sync and everything, and all the work that goes into that, and then all the satellites that transit what do they call them, DGPS stations. Whenever they transit two of them, they get a signal sent to compensate for the timing difference, to correct for their clocks, to keep them all in sync together. So it's really a cool effort in how they do it, to maintain the accuracy of it. A very cool project.
You mentioned something a minute ago about it being able to work on a flat Earth. I'd like to see some evidence of that, because if you look at the geometry of the transmissions and the ephemeris, it's in a Cartesian coordinate system. So there's no stellar-based references until you go to turn it into a lat long elevation. And all that solution to the position happens in that Cartesian framework. And it clearly won't work if the framework is not correctly spatially oriented. If the distances aren't correct, you won't be able to solve for your position and solve for a position just next to you and get a coherent result. it can only work if the satellites say where they say they are, when they say they are.
Well, when you get into the corrections that they have and how they work out, like specifically for let's take the analysis that they give us for the orbital parameters for the satellites, where they say special and general relativity would cancel out each other, or would cancel each other out at an orbital altitude of 20,000. What is it? 20,000 kilometers. So if you have that, and you have a timing difference that is derived from the Sagnac effect, which is what they end up correcting for everything. Because like I said, they don't use relativistic transformations; they just use classical equations. So they end up using a classic equation that's equivalent to the Sagnac effect to account for these. And anyway, when you take that orbital parameter, right, that timing difference, right, instead of having it be 20,000 in altitude, if it was closer, but it was going around in a circuit around a flat Earth at 20,000 kilometers, you could share that, or you could have timing difference corrections where it would be essentially simulating that relationship covariantly. So the satellites or whatever, right, would clear the sky in the same amount of time. They're just closer, moving faster, or I mean, sorry, moving slower. But due to the timing offsets that are sent out, right, the way that you interpret it, it's going to be through the coordinate system that it's already been specified to with those parameters. So it's going to be just as valid because it's timing corrections that are being made that are changing how they're accounting for distances. So when you say that it couldn't be valid how? It's all facilitated through timing corrections. That's what makes the accuracy to it, comporting it to a specific coordinate system. And not, so that's my argument to it.
Yeah, so a couple of things for that. So first of all, we can do a completely uncorrected GPS location. We can solve for pseudo range in the ECF frame. We won't work out what the actual time is, but we can actually get a position without applying any corrections. And that's so those timing differences and the adjustments you make to the timing for relativistic reasons or for atmospheric propagation reasons, those timing things are physical properties of the transmission path between the individual receiver and the satellite. They're not adjusted for any individual. The timing on the satellite is adjusted to keep it in sync. So, it's not perfect, it drifts, there's perturbations to the orbit. There's no way that the ephemeris that is sent could give meaningful locations to anybody unless it is actually following that path in a geometric space.
So not understanding the significance of the meridian corrections that they do to the speed of light, like when that guy went in to go get the quote unquote raw data and it was already corrected, right? And like in the meridian corrections that they make for the satellites to keep them all in the same time so that everything is relative to the coordinate system is going to be the exact mechanism as to why you would never know. And the phase carrier and what was the other thing you said? The pseudo range carrier are not the raw data. Those are not what you would need to substantiate the actual raw data. What you're being sent is going to be useful for that coordinate system that's already been corrected. You do not get to have the actual information. So that's my point of contention.
So what
That's
is
where
this raw data?
that's where we deviate. That's where we deviate on it.
Yeah. So I've heard this raw data mentioned before, and I've seen references to it in that paper, but nobody could really explain what they were expecting from the raw data. So if you capture and decode the raw GPS signal information, there's nothing in there specific to you, right? That is just what you get off the air. And you can take that, you can capture that information, the phase information and the timing, and go away and calculate the position offline, right? So there's nothing special about you in any of that information. The only difference between you and another observer is the time of flight of that message. And yeah, if those messages don't come from where they say they're coming from, for everybody that can receive them, the system will not function.
Yeah, so they were specifically time of flight corrections. What they would have observed in the analysis, similar to what they would do for sonar and sound waves, you could backwards derive c plus or minus v out of that to get the distances, and it should come out c as being c, but it doesn't. So that's the issue. Now, when they said that, oh, well, these corrections were just due to the Sagnac effect, which is a second order Doppler shift, which is an incorrect assertion about what the Sagnac effect is. It's a first order timing difference, not a second order Doppler shift. And so that the corrections to that are specifically the mechanisms that would obscure any or that would make it so that you wouldn't be able to tell the actual positions of anything, but everything would still work out and give the appearance publicly that that's what how you're using it would be.
Yeah, these corrections are all applied receiver side. So the clock and the messages are fixed, right? That they get adjusted periodically, but the message being broadcast and the clock on the satellite is effectively a free running sequence of messages. All of these corrections happen in the receiver. And if you choose not to apply any of these corrections, you can still get a fix that places you relatively close to where you expect to be. It's the corrections, and whether you believe their nature or their correctness, these corrections that are now sort of standard through most GPS stacks, are what turn a course location, 100 meters or whatever, to a few meters. And in the case of real-time kinematics, you effectively get to bypass all of those corrections because you're able to have a difference between a known fixed location and a moving GPS receiver, and eliminate any issues about the origin of the corrections by calculating them on the fly.
Listen, we're talking, first of all, primarily about two separate sets of corrections. One, we're talking about relativistic effect corrections that aren't manifested. The second set of corrections that we're talking about are meridian corrections, which are in the same respect that the so-called relativistic corrections would be timing corrections to the speed of light. So if we're using a system that's making corrections to the timing speed of light that are meridian corrections, right, that are latitude and longitude dependent, we're not going to be able to use it to falsify the system, and it's going to give you the exact output of what you're expecting to get is. Now, the secondary corrections that you're applying to from the receiver end is what you would say would be like Earth rotation, or I would say ether drift relative to the latitude. So that is what the other correction that you're referring to that would bring your pseudo range and your range carrier estimation into alignment with your actual position. Because like you were saying, if you don't account for that, you're going to be off by about 30 meters or so, right? So what I'm saying here is that the corrections that exist within the system to make it work already make it so that we wouldn't be able to verify or assert anything about its corrections or correctness in terms of like where the positions of these things actually are. It's going to comport to what it would appear to be with a like fake coordinate system overlaid with just timing offsets to make it compensate to the same thing. When GPS was originally given out to the lads and ladettes, it had a mechanism in it that could be you can change the way that the receivers would get derived distances based off of the signals that were sent, and it would be inaccurate. And they said that it would help prevent like terrorist attacks, and so that you couldn't use GPS guided stuff like that. So the idea that they can't do corrections or send out signals that aren't correct, I mean, it's just like I don't want to continue that line of argumentation. So like if you want to get like a final thought off, we can move on.
Yeah, so what you're describing there is selective availability, where they would deliberately introduce timing errors, which would increase. So when you do a GPS fix, it's not just one solution to the problem. You have a continuously, you're iterating over time to refine your position, and as you improve estimates of things, you get a closer and closer fix. And you can see this as you watch your phone. It gets more satellites, it gets more information, and your fix gets tighter and tighter. So selective availability introduced random variations in the P code phase, so that you had large uncertainty in your measurement at all times. But the key thing that I want to emphasize is that if they've adjusted the timing for someone that's 500 k's or say 2,000 k's downrange of the satellite, is approaching them from 2,000 k's away, That same timing information has to work for somebody that's 2,000 k's on the other side, or 2,000 k's north, 2,000 k's south. So the timing information cannot be specific to a user. It has to work for everybody, right? And if it's wrong, it'll be wrong for everybody. That satellite won't be useful in a fix.
Alan, if you want to take a look at my screen for a second, I was looking at the author of that article you're talking about. This gentleman, Royoung Wang, he published something, and if anybody else cares to look at my screen as well, he published something in 2006.
It's a great paper. The
A
phase
follow-up.
conjugate mirror.
So a follow-up to this, he argues that if you, right here, if we have a method to change the positive phase shift to a negative phase shift, the first order effect will augment each other instead of canceling each other. So he's arguing the opposite. In this case, the first two order terms, 2 pi L over 5 VC, in Michelson-Morley experiment no longer cancel each other out, but augment each other. Then we'll have a first order experiment. Actually changing a positive phase shift into a negative phase shift is what some PCMs can do. So he's arguing, he kind of iterates on his first explanation and follows up with this to kind of argue the opposite, is what it's seemingly saying to me.
No, he did that before he did the linear configuration anyway, if I'm not mistaken. And then what they showed with the phase conjugate mirrors is that the one-way speed of light, because the big contention was that you can't know the true one-way speed because when the light hits the mirror, it'll change the wavefront. So we need to measure it before it changes it. But the phase conjugate mirrors preserve the wavefront orientation. So it's kind of like sending it backwards in time. So what they did with that was he showed that, the speed of light already changes on the one way.
Yeah, and this is the only two things I could find from him. I could find this.
Oh, he's got a ton of stuff I can send you. If you, he's
Does
got
he?
if you type ResearchGate in his name, all of his stuff is on his ResearchGate.
Is it? I was just looking up his name.
Yeah.
And this was from, well, a seemingly different source, from 2006, right here.
Oh no, so that
Let's
would have
see
been
here. Yeah.
after his that would have been after his.
Yeah, that's what I'm saying. And he had another author on this as well. But I just thought that was kind of interesting. I don't have a deep level understanding of this. I'm just curious about this guy. But yeah, I would be interested in I guess the technical way how they correct it, but that's kind of a separate secondary thing, so we won't get into that. Well, that's all I had though.
Cool, no worries.
I definitely wanted to highlight a point that was brought up early, specifically around a specific point. In the instance of time dilation specifically, somebody brought up predictive power. It's less about predictive power implying correct interpretations of relativity. It's more about if you have alternate interpretations that have the same predictive power, that meaningful interpretation, specifically in setting clocks in motion relative to a medium, has a more meaningful interpretation than, let's say, Lorentz transformation that that's relative to observers that adjust time itself. Would that be accurate, Alan?
Yeah. Yeah, because so their relationship with like their step into covariance was like, okay, so as long as we say that time and space change symmetrically, we're good to go. We don't have to use absolute time and space anymore.
Correct. So predictive power in and of itself doesn't imply correct interpretation of reality. It's what has meaningful interpretation. So yeah, thank you for clarification.
I know you've been through the idea of, I guess, what we call spoofing for GPS. And there's a whole presentation you did on that you can refer others to. It got left off a little bit with what Dazza was saying, as if he were asserting there'd be no way for GPS not to be from satellites the way we think that they are. And just for anyone listening, they can refer to Alan's channel on breaking that down and how that seems to might have been done as far as giving us the data from a certain distance that may not be exactly what they're saying. Layman's way of wording that, I guess. Right?
There's no doubt GPS can be spoofed, right? It can be spoofed over small areas, but you can't spoof it for everybody all the time, because of that timing information, right? The bigger the area you try to spoof, the more impossible it becomes, because you have to maintain consistent timing across the entire area, and it's not feasible to do more than a local spoofing or a local disruption.
That's what you think, at least, right?
Oh yeah, and it's demonstrable, right? That you can go and plonk a GPS receiver down anywhere.
It's pretty fair.
And,
I was gonna say it's pretty fair. My contention is that it's corrected and offset before it's sent. Like what you're getting is already cooked. That's what I would say.
Cooked for everybody that can receive it, right?
Yes.
Yeah.
Can I make a
Which means it
statement?
has to be correct, all right?
There you go.
Yeah.
There you go. That's how it's done, probably.
Well, they already do that too with the meridian corrections. That's what I'm saying. Like either like independent of how we think, conspiratorially, or just thinking like, just to get this thing to work, you would still have to do that. Like what they've done, they would still have to do. The thing that I'm bringing up is more about the relativistic aspect of it and how it falsifies relativity theory, because it shows that the speed of light isn't constant.
Maybe you can point on the slides, on Alan's slides, where he got wrong.
No,
That might be helpful for the audience.
He didn't. That's not that kind of wrong.
Yeah, I'm not disputing that the relativistic corrections and their explanation and physical interpretation might be under dispute here. I'm not an expert in relativity, but I do know that the corrections that are applied on the receiver side work. Whether they work because of relativity or because of some other reason, it's up to you guys. But GPS does work and work very well. My main contention here is that the clock corrections and the ephemeris corrections are fixed for a long period of time. They're valid for up to 14 days, and they are not adjusted for individuals. So if the GPS clock is wrong, that GPS satellite will eventually become unusable.
Pre-cooked.
Yeah, but New Perspective, you can test this, right? You can get the pre-cooked. So you can record the live signal from a GPS satellite. You might want to do a bit of pre-processing of it, but rather than record the radio signal directly. But you can get a receiver, or you could even build a receiver, right? Because it's open enough that you're allowed to do that. And you can record the signals, say, in, California, and you can go 1,000 kilometers, 1,000 miles up the coast and record the signals again. And you can, or at the same time, then you can come and compare those two sets of signals, and you'll see the information coming to both locations is identical. The only difference is the timing between the arrival of those signals, which gives you a different location. There's a heap of stuff you can do to verify it yourself.
Yeah, well, whatever's being done, if it's not exactly what we're being told, it would be very, very intricate and complicated way of making it seem as though it's exactly what they say, right?
Yeah, but at the end of the day, it's a relatively straightforward thing that is going on here, and it's quite easy to pick up flaws and inconsistencies in the data, because your location and locations nearby will not be consistent.
When you run this test, and I don't know if this plays a role in it, but I mean, is this raw data that you're receiving from the satellite, essentially, that you're saying? Like you said 1,000 miles away or something. I'm just kind of looking for where the correction may be occurring.
Hey, real quick before we go down the GPS superhighway, let me wrap up it's all good. Let me wrap up the Prezi. So I hope you guys all enjoyed the history on the physical interpretation of mathematics, going through the classical, going into the relativistic and where they differ. And if you guys have any questions, feel free to ask or email me later. That's it. I'll be back in a few minutes. I'm going to close out the stream.
Awesome. Thanks, Alan. That was awesome.
All right, lads and ladettes. What do we got coming up for tomorrow? We have Globebusters. We'll be doing a Prezi on Globebusters. And then Shane will be covering Eratosthenes on Tuesday. Make sure to stay tuned in for that. And then we'll see what the rest of the week has in store for us. Later, guys.